Okay, this is the second video about IB thermodynamics, and we're looking at states of matter and phase changes. So there are three main states of matter you need to know about. The first one is a solid, which has a fixed shape and a fixed volume, meaning if something's a solid, it doesn't change shape if you put it in a different container. And what it is each atom is held in approximately the same place within a crystal lattice. And there are forces that exist between the adjacent molecules in the crystal lattice that can be approximated by little springs, which means that each atom here is going to be kind of jiggling back and forth a little bit in 3 dimensions, although you don't really need to worry about that, on the springs connecting it to its neighbors. And the result is that when you calculate the internal energy, you have to consider both kinetic and potential, because there's potential energy that's stored in the springs. You won't actually need to calculate it, but you do need to know that there is both kinetic and potential energy. And there are strong forces between molecules. Now in a liquid, you have fixed volume, but it has changeable shape. The idea is that the molecules are still packed close together, but the bonds between them are no longer as strong, so the molecules can move long distances. So there are only weak forces between molecules. And there is still kinetic and potential energy in the internal energy, but potential energy is less important for liquids than it is for solids. Now gases, which are the phase of matter we're going to spend most time on, mostly because they're the easiest thing to calculate for, have a changeable shape and volume. If you force a gas into a large container, it will expand to fill the shape of that container. If you compress it into a smaller container, the volume will change to fill that small container as well. And the gas molecules move at relatively high speed, and we say that there are no forces between molecules except in collisions, and also that the internal energy is only kinetic. So there's no potential energy at all. And so if you look at a phase change being a transition between two of these states, there are several different kinds. There is sublimation, which means solid directly to gas. There's boiling, which means it means liquid to a gas. There's condensation, which can be used to describe a phase change from a gas to either a solid or a liquid, depending on the context. There's also freezing, which is a change from a liquid to a solid, and melting, which is a change from a solid to a liquid. All of those require energy inputs, or energy taken away. For example, for boiling, you're adding energy in order to break the bonds that connect the molecules. And really that's what you're doing. You're either adding energy to break the bonds or taking energy away so that bonds can form again. Now the difference between boiling versus evaporation is that in boiling, all of the liquid turns into a gas, whereas in evaporation, the high temperature molecules escape, leaving the lower temperature molecules behind, with the result that the liquid left behind is actually cooler than it was before the evaporation occurred. And you do need to know the difference in boiling versus evaporation. Now, let's take, for example, melting. In melting, you add energy to break the bonds that hold the molecules in the crystal lattice. And the reverse of that, freezing, you take energy away, which means that those bonds can reform again. Essentially, you are increasing the potential energy. The higher the potential energy is, the weaker the bond is. And the thing that happens here is that temperature is constant during a phase change. So while something melts or boils or condenses or freezes or melts or sublimates, the temperature of that substance does not change. That's because temperature is a measure of the average kinetic energy. But during a phase change, the energy that you add changes the potential energy, not the kinetic energy. So when you add energy, let me write that down, during a phase change, the potential energy is increased, not the kinetic energy. So when you add energy to a substance, one of two things can happen. You can either increase its kinetic energy, which means increasing its temperature, or you can increase its potential energy, which means phase change. You can't do both. So what will happen if we make a graph of, if we take, let's say, ice, we start out with ice, we gradually add heat to it, and we'll find that because of that, the temperature will increase. But then, the temperature will stay the same for some time, even as we're adding more heat, at which point, after that, the temperature will rise some more, and then it will level off, and then after another level segment, the temperature will start going up again. So what happened here is that we started with ice, so this is a solid, and then in this time here you have a liquid. During the time when the temperature stayed constant, you had a phase change. So the whole thing stays at the same temperature, but as you move along this line, more and more of it changes from a solid to a liquid. Once all of it's turned into a liquid, the temperature can start going up again. And if you want to use this graph to find the melting point, well, it's just the temperature at which that occurs. And then it's a liquid. And one thing you can say about this is that the slope of this line is equal to 1 over the heat capacity, which is interesting. And so the liquid is increasing its temperature until it gets to the boiling point, at which point the temperature levels off again. And while the temperature is leveling off, or while the temperature levels off, now as you add heat, it causes more of the water to change into a gas. And then once all of the water is changed into a gas again, the temperature starts going up again. And so graphs like this are very, very important. You can do a lot of calculations from them, and test problems frequently do ask you to do that. You should recognize that these places where the temperature levels out, even though you're adding heat, is when a phase change is occurring, and you should be able to calculate the heat capacity based on the slope of the line while it's a solid or a liquid or a gas. And now, what we do need to calculate is this idea of latent heat. Latent heat is the amount of energy necessary to boil or melt, depending on what it is, 1 kilogram of a substance. Now, if you're talking about boiling, you'll call it the latent heat of vaporization. And if you're talking about melting, you'll use the latent heat of fusion. And those will generally not be the same for any given substance. So let's look at this example where we have a heat supply that provides 150 watts of power. That means it's giving us 150 joules of heat every second. The question is, how long will it take to boil 100 milliliters of water if the water starts out at a temperature of 20 degrees Celsius? Now we know that when we add heat to a substance, we can either increase its temperature or we can change its phase. So before we can make this change phase, we need to raise all of it to the boiling point. So heat to raise to the boiling point is given by mc delta T, and the mass of the water is 0.1 kilograms. The specific heat of water is 4.186 kilojoules per kilogram Kelvin, which is different because I'm using kilojoules instead of joules. We'll see why later. And the change in temperature is the final minus the initial. So an 80-degree temperature change. And that works out to be hold on a second. That works out to be 33 kilojoules, 33,000 joules of heat. And you think that's a lot. But then you go to calculate the heat to change the phase, to actually make it boil once it's at 100 degrees Celsius. For that, we use the equation Q equals the mass times L, which is the latent heat. And I'll write that equation up here. So the amount of heat you need is the mass times L, where L is the latent heat. And that works out to be 0.1 kilograms. And then we need to look up the latent heat of water, which you can do in your textbook, or you can Google it. If you need it on a test, you'll be told what it is. But the latent heat of water is 2,260 kilojoules per kilogram. And that means that the amount of heat it takes to boil this, once it's been raised to 100 degrees Celsius, is a further 226 kilojoules. In other words, about 8 times as much energy as you needed to heat the water. And then the total energy required is 259 kilojoules. And now we need to ask, well, how long does it take for us to produce 259 kilojoules of energy? So we'll remember the definition of power, which is what we measure in watts. Power equals the work or the energy transfer divided by time. And so to find the time, we take the amount of heat that we added, and we divide that by the power output. So 259,000 joules divided by 150 watts gives us 1,730 seconds, which is right about 29 minutes. That's to boil all of it off. Now, to start the water boiling takes much less than that, but if you wait till all of it's boiled off, it will take almost half an hour. So for this video, what you need to know is a description of each of the phases of matter, and you need to be able to calculate how much heat it takes to change a phase.